So let's quick review what the first two entries should be in your test. You should have the first row should be the nth term test. And the nth term test only tests for divergence. It's inconclusive if you get anything else. So the name of it is the nth term test. We take the limit of the nth term, and if the nth term is the limit is anything other than 0, that tells us the series will diverge. It's the quickest way to tell divergence. If the limit of the series is 0, it's inconclusive, and you need something else. So then the second, so let's do that quick just as a review. Okay, we're going to set our things up today. So we'll take the limit of the nth term. So I'm going to say, okay, the limit as n approaches infinity, checking this first, 3 to the n over n plus 2. That would be 3 to the infinity over infinity plus 2, which is infinity over infinity. So then what do? Which is what rule? Okay, so then we need to apply L'Hopital's. So we'll do a quick L'Hopital's to this. The derivative of 3 to the n is also 3 to the n times the ln of 3. And then the derivative of the denominator is 1. Then we get 3 to the infinity times ln of 3, which is a defined value of infinity. But the important thing is not what it is, it's what it's not. This is not equal to 0. And so since the limit of the nth term is not equal to 0, we can conclude that it is divergent. That's the only safety net you have. If it's not 0, it is divergent. So then our sample of our second one is what happens when it is 0. So the limit here, 2 times n over n squared plus 3, we'll get 2 times infinity over infinity squared plus 3, which is infinity over infinity, which means we have to go back to L'Hopital. And the numerator becomes 2, and the denominator becomes 2n, which reduces to 1 over n, which simplifies to 1 over infinity, which is 0. And so our conclusion is inconclusive. So that's why we needed to introduce another test. So moving on, we introduced test 2. Test 2 was, okay, if it's geometric, so the next row, the next entry for yours should be the geometric test. And this can prove both convergency and divergency. So this works for a geometric series or a geometric power series. Geometric series would be if the multiplier was a constant. Geometric power series would be if the multiplier included a variable. So this should be your next entry. If we can prove that the ratio is between -1 and 1, then we have a convergent sum. If it's outside of -1 or 1, or even equal to -1 or 1, then it diverges. Okay, but not every series is geometric. So this is where we get to what we're going to talk about today. We need another test if it's not geometric. Okay, so that's our goal, is to walk out of here with a third test for something that was inconclusive with an nth term and is not geometric. So introduce test 3. So your next one will be the ratio test. The ratio test. We also use a limit here to do that, but there is a requirement here. The requirement is positivity. This does not work with anything that has negative terms. Okay, positive terms only. So in other words, if your series alternates, this test will not work. only works on positive terms. All right, what we do is we don't apply a limit to the last term. We apply a limit to the last term and the second to last term. So I want you to look at what this looks like. It actually works for any two terms. A sub n is the nth term. A sub n plus 1 is the term that comes after that. So you pick an a sub n term, just an arbitrary a sub n term, and then you also find an a sub n plus 1 term, and you take the ratio. That means you just do a numerator and a denominator, and you find what we work out and find out the limit, just with our limit work. So I'll show you how to do that. But let me tell you how to read the results. If the result, L, is less than 1, so if L is any number that is less than 1, the series will converge. 2/3, pi/6, okay? Any number of value that's less than 1. The series will diverge if the numerical value you get is anything greater than 1. Pi, square root 2, 10, anything greater than 1. So what's the only other option? If L is equal to 1, then we are still inconclusive. So this works really, really well on two different kinds of problems. It works great on exponentials. And it also works really well on factorials. Now, we've spent a lot of time devoted to exponentials. Factorials are not something that we've spent very much time in. In fact, I'm not even sure everybody knows what a factorial is. So let me quick review that. A factorial would be n with an exclamation point. So if I asked you for 4 factorial, do you guys know what that means? Yeah, it means 4 multiplied by 3 multiplied by 2 multiplied by 1. If I ask you for 10 factorial, it's 10 times 9 times 8 times 10, it's all the way down. Okay, it's a string of multiplications. You can either go either order. You can start at 1 and end at the bigger number, or you can start at the bigger number and go down to 1. But either way, that's how factorials work with multiplication. So one quick thing is like to check if somebody understands, you might be asked, what's 7 factorial divided by 5 factorial? And I do it without your calculator. Well, the understanding of that is that this is 7 times 6 times 5 times 3 times 2, 4, whoops. How about we get 4 in there? Times 4 times 3 times 2 times 1. And then the bottom one would be 5 times 4 times 3 times 2 times 1. So how quickly can you tell me what the answer is? 7 times 6, which is 42. So if you know what factorials are, then they reduce really well when you understand the concept and you're able to simplify and come up with the answer of 42. All right, we'll talk about that too. Okay. I'm going to apply this, what's called this ratio test. The ratio means we're creating a numerator and a denominator. So let's make sure we understand what the terms are. A sub n is any arbitrary term. And so the formula for a sub n is 2 to the n over 3 to the n plus 1. It's what we were given. That's your a sub n. But I need you to understand what a sub n plus 1 would be. What would be the next one in the sequence? Well, you got to add 1 to all your n's. So that term would be 2 to the n plus 1. That's the next one. We're adding 1 to every place we have an n, and 3 to the n plus 1. And then I still have a denominator of just plus 1, because I'm not adding 1 to that, because it didn't have an n in it. These are the two terms. An arbitrary nth term, which is defined, and the next term we get by adding 1. Will this always make positive terms? Okay, well, the number 2 is positive, so anything 2 to the nth power is going to be positive. The number 3 is positive, so anything 3 to the nth term is going to, and 1 is positive. So positivity is guaranteed. So you have to like state that. Since all a sub n terms will be positive or greater than 0, we can apply the ratio test. If any of the terms happen to be negative, the ratio test is going to fall apart and it won't work. So the ratio test says, take the limit as n approaches infinity and stack or ratio these two terms to each other. So take 2 to the n plus 1 over 3 to the n plus 1 and do it in ratio to the other term. Now mathematically that looks awkward because you've got two numerators and two denominators. So what would be a better way mathematically to write that? So instead of making this division thing, we want to multiply by the reciprocal. Good. So what we'll do is we'll make this, okay, I'm going to put 3 to the n plus 1 here, and I'll do 2 to the n there. So I'm multiplying by the reciprocal instead. The rest now becomes straight out algebra. So I am checking what this will simplify to be. So what I want you to do is, which you can because this is multiplication, I want you to regroup the like terms with each other. So put the 2's in ratio to each other and put the 3's in ratio to each other. When you do that, some of those terms can reduce. The 2's can reduce, the 3's can't. What stops the 3's from, the 3 term from being reducing? The plus 1. You can't reduce when you've got this plus 1 hanging out here. That stops you from reducing, but I can reduce the other one. Yeah?
Why did it change from limit as n versus 2?
Oh, I just didn't finish my thank you. Good catch, good catch. All right, so let's focus on the 2's because we can reduce those. Which is bigger, the numerator or the denominator? The numerator, right? By how much? Yeah, but in this case, by how much? By 2. It's bigger by a factor of 2. So like if the denominator was 2 to the 3rd, the numerator would be 2 to the 4th. If the denominator was 2 to the 11th, the numerator would be 2 to the 12th. So it's only, so is that reducible? Sure. Okay. And when we reduce, what do we do with powers? What's the rule? Remember, Edson, you were saying you forgot what to do that one on that thing. What do you do with powers? You subtract, and what are you going to be left with? 2 to the 1st. So when we reduce that, we are just left with 2 to the 1st. 2 to the 1st is a constant, and where can we pull constants for limits? Out to the front. So we will be taking the constant of 2 and pulling it out to the front, so we only have to focus on the what's left. Now I can't reduce this term. So I plug infinity in. That'll give me 2 times 3 to the infinity plus 1 over 3 to the infinity plus 1 plus 1. That's infinity over infinity. So I need to go back and use L'Hopital. So I'll go back to my limit. And I'll use L'Hopital. So L'Hopital says the derivative of 3 to the n is still 3 to the n times the natural log of 3. And the derivative of, and the plus 1, the derivative of that is 0. And then the derivative of this will be 3 to the n plus 1 times the natural log of 3 and then plus 0. This is now reducible because I just got rid of the plus 1's. The plus 1 is gone. I can reduce again. So I can reduce the natural log 3's for sure. And I can reduce these powers. Now there's an extra 3 in the denominator. So this becomes 2 times the limit, and all that's left is 1/3. The ln 3's are gone. The 3 to the n and the 3 to the n minus plus 1 subtract. I'm left with, so the answer to this is 2/3. So then we have our final conclusion. Since L turned out to be 2/3 and 2/3 is less than 1, we conclude that the series converges. All you have to do is come up with a number that's less than 1, and then the series will converge. So this is just algebra heavy in terms of reducing, separating your terms, but all you gotta do is see what the number turns out to be. So that's the first time you've ever seen that. Okay, Jonathan, am I going too quick or are you catching up okay? Okay, all right, let's try another one. So what about the convergence or divergence of this series? Again, we want to check the positivity first. So that should be the very first thing, like on an FRQ, right out of the gate. You're going to say, since all a sub n is greater than 0, in other words, all terms here are going to be positive. Why? Because 4 to the n is positive, and n itself is positive, and 3 is positive. So since they're all positive, we can apply the ratio test. All right, our terms are going to be, the a sub n term is 4 to the n over n plus 3. The a sub n plus 1 term means I have to add 1 to all the n's. That'll be 4 to the n plus 1 over, and I have to add 1 to the n in the denominator as well, so that'll be n plus 1 plus 3. So it turns out to be 4 to the n plus 1 over n plus 4. All right, so we apply the ratio test, which says, put the a to the n plus 1 term on the top and reduce it or take the ratio with the a sub n term on the bottom. So always start with the a plus 1 term and a to the n plus 1 term, a to the sub n plus 1 term. So that would be 4 to the n plus 1 over n plus 4. And then I don't mind if you jump right to the reciprocal step. Instead of showing the division, you can go ahead and multiply by the reciprocal. So the reciprocal would be n plus 3 over 4 to the n. And then at that point, I'd say, okay, rearrange and put the like terms. Because you're in multiplication, the order in multiplication is, we can do it in any order, so that's commutative. So then we'll have 4 to the n plus 1 in ratio with 4 to the n, and then we'll have n plus 3 in ratio to n plus 4. You can't reduce the n plus 3 and the n plus 4, but you can reduce the 4 to the n plus 1 and the 4 to the n. So these will reduce, and you'll be left with the constant of 4. So 4 can get pulled out. And then I just have to focus on the n plus 3 and the n plus 4. Those are infinity times infinity, which means I'm going to need L'Hopital to finish this. So 4 times L'Hopital, and L'Hopital gives me 1 over 1. So the answer to this is the constant 4. All right, so Juliet, since the answer is 4, what's the conclusion? So since the limit value is equal to 4, which is greater than 1,
The series diverges.
yes, the series will diverge. So we've seen one where it was less than 1, so the series converged. We've seen one where the limit value is greater than 1, so the series will diverge. And remember, if you get one that's equal to 1, it's inconclusive, which means we're going to need another test that we will add in the future. All right, so needing to talk about some factorial. Yeah.
This one will tell you what it converges to, right? It just tells you whether or not.
Correct. This is not telling us what it's converging to, just that it does converge. The only one that we can tell what it will converge to is geometric, either geometric straight or geometric power. Those are the only ones. All right, so let's talk a little bit more about factorials. So we've defined factorials as the following. It's n times the number that comes before n. What's the number that comes before n? N minus 1. And what would the number be that comes before that? N minus 2. And then all the way down, and eventually you get to 3, 2, and 1. It doesn't matter to me if you want to go the other direction. If you want to go 1, 2, 3, and then end up with n minus 2, n minus 1, and end with n, that would be fine. So if you had n plus 2 factorial, that means you've got to start. I usually start with the biggest one. The biggest number would be n plus 2. And then before that would have been n plus 1. And before that would be plain old n. And then before that is n minus 1 and n minus 2. And then I get eventually down to 3, 2, and 1. No, it really doesn't matter to me which direction you want to do it, whether you want to go from big to small or small to big. Having that understanding is going to help you determine the divergence or convergence of a series that has factorials in it. All right, here we go. So we're ready to start off with this one. We just have to check the positivity. So we know that 2 to the n is always a positive number. We know that n plus 1 factorial will always be a positive number because you just start with n plus 1 and do all your factorials down to 3, 2, 1. You never get negative numbers. Same with the numerator. All factorials are positive numbers because you never get lower than the number 1, so you never get to negative. So that guarantees us positivity. So since a sub n is guaranteed to be positive, we can apply the ratio test. A sub n will be the given term, so it'll be n minus 1 factorial over 2 to the n and n plus 1 factorial. A sub n plus 1. I need to add 1 to every n in the equation. All right, so Rain, add 1 to the n in the numerator. What will you get?
N plus 1 minus 1, so just n.
Yep, I just get n factorial. Okay, Alex, add 1 to the different n's in the denominator. Okay, 2 to the n plus 1, all right? Yeah, n plus 1 plus 1, so n plus 2 factorial. All right, so now that we've got our terms, we can take the test, which is going to be the ratio of these terms to each other. So we start with the second one. We'll have n factorial over 2 to the n plus 1 over n plus 2 factorial. And then I'll multiply by the reciprocal of the other one. So 2 to the n n plus 1 factorial over n minus 1 factorial. And then I always line up and I group my terms that are similar to each other. So I'm going to start with the 2 to the n over 2 to the n plus 1, because that's always an easy one for me to do. I can see that it's going to reduce, and I'll be able to pull a constant out to the front. In terms of the factorials, I tend to group the factorials together that are closest to each other, but there's really no right or wrong way to do it. So I'm going to group, and I'll circle them in green. I'm going to circle n, and it's closer to n minus 1 than it is to n plus 2. N plus 2 is 2 terms away, whereas n minus 1 is only 1 term away. So that's what I tend to do, is group those together. So I'll have n factorial over n minus 1 factorial. And then the other two I would group together, and I'd have n plus 1 over n plus 2 factorial for both of them. So now we need to talk about reducing. So you've seen the exponential ones reduce. So as we focus on reducing these two, what constant will I be left with? 1/2. I have more 2's in the denominator. I've got an extra 2 in the denominator. So I will be, I have the constant 1/2, so I can pull that out. So I'll have 1/2, and then I'll have my limit. All right, now I want to look at reducing the next term. Okay, which one of those is longer than the other? The numerator, why?
Because n factorial will be n times n minus 1 times n times 2.
Okay, so the numerator would be n, and then n minus 1 and n minus 2 all the way down to ... 3, 2, 1, whereas the denominator is going to start with n minus 1 and then have n minus 2 and go down to all the way down to 3, 2, and 1. So they have almost all the terms in common, except the numerator is longer and the numerator has this extra term. So all these terms are going to reduce the entire denominator, and all we're left with is n. Okay, for this second one, so Jonathan, as you're looking at the last set of factorials, which one of those is longer?
N plus 2.
Okay, and what's the term it's longer by?
It's going to reduce to 1 over n plus 2.
It's going to reduce to 1 over n plus 2. You're exactly right. So we're going to have, this one would have been n plus 1, and then n came before that, and then n minus 1, and then all the way down to 3, 2, and 1, whereas this one would have started with n plus 2, and then started with n plus 1, and n minus 1, all the way down to 3, 2, and 1. So when we reduce the entire numerator, and we reduce all but n plus 2 in the denominator. All right, so we are left with a limit that has n in the numerator and n plus 2 in the denominator. We're in the home stretch. This will be 1/2 times infinity over infinity, which means I need to go back to L'Hopital, which will be 1/2 times the limit of 1 over 1. And I take my derivative, and I get 1/2. All right, so Rain, give me a conclusion. Since
L equals 1, the test is inconclusive.
L doesn't equal 1.
Oh, sorry.
Ooh, you were close. You forgot about what we had out in front.
Sorry.
All right, so since L equals 1/2, which is not 1, but is,
Less than 1, then in conclusion.
okay, then the series converges. But you would have been right. If it had been 1, it would have been inconclusive. So if it does end up to be inconclusive, then we will be learning additional tests to handle that. as we kind of work through the funnel of our work.